Okay, we have two topics today. I'm going to start with missing values, particularly because missing values for multivariate data are tricky. It complicates many things. And so having ways to assess the structure of the missings and also the way that the missings are imputed can help in improving your results at the end. So we'll spend a little bit of time on missing data, and then the large chunk of the morning will be on cluster analysis and on methods for evaluating the clustering algorithms. Okay. So a couple of pieces. There's some language for missing values. Actually, I think there's another workshop happening on missing values right now. So 3 days of missing values instead of 30 minutes of missing values. But the main terminology, missing completely at random, missing at random, and missing not at random. Terrible names. Terrible names. But there's some rationale to the type of missing. So missing completely at random means that the missings are just missing all over the place, and there's no main mechanism to the missings. So there's no dependence between missing and not missing and any other variables. Missing at random means that some of the missing values depend on other variables. Particularly if your recording equipment fails when temperature increases, you may have more missing variables at the higher temperatures. Okay? But it still is information that you have in the data, and that because you have information, I'll wait a couple of minutes. So with the missing at random, because we have that information in the data set, we can use that information to impute missing values. Right. Missing not at random is a much more difficult case. So you have some missing structure. It's clearly not missing at random, and it's not missing on information that you have. It's clearly got some dependence pattern with other information that you haven't collected. And so it's almost impossible to do anything with that type of data. So it's really these first two, missing completely at random, missing at random, that we can do fairly well in terms of imputing missings. One of the main reasons why you have to consider imputation with multivariate data is that any missing values often mean that you have large chunks of your cases missing. So you may only have 5 missing values, but they might be on different variables and different cases, and that means that if you want to ignore the missings, you're going to be throwing out a lot of data. So generally with multivariate data, you can't easily ignore the missings. You need to do something with them. What we do is build a shadow matrix, something called a shadow matrix, which just masks what's missing and not missing, and that way we can always keep track of the missing values. And then we use that to look at different ways of imputing and see which one is, visually the best, right? Visually, it works out the best. Okay, so those are the 3 pieces I want to cover. The shadow matrix. So here's a short example. I just have a data set with 10 cases and 5 variables. And I only have 5 missing values in here. Right, so NA means missings. That's the R convention, to use NA for missing value. It's a nice convention because it forces you to handle the missing somehow and be aware that you've got missings in your data, rather than make mistakes of making averages with some strange numeric variable numbers. So you can see there's only 5 missing values, but they're on the first 5 rows. And so if I ignored those missings, I would only be using 50% of the data. Right? And I have a missing on every single variable, so I'd be throwing out all the variables as well. So that's my data. The shadow matrix, just a binary matrix, zeros and ones. 0 means complete, that the value's there. 1 would mean it's missing. You could use true or false. You could use a logical variable, true or false, would be fine. You could extend these ideas also to have a different indicators for types of missing too. So you may have sensor data or you may have other things. So you could use this idea for other types of data as well. Alrighty, so that way once we start imputing values, we can always keep track of which ones were imputed. I'm going to use a very short example for a couple of slides. This is climate data, well, measurements on from buoys in the Pacific Ocean that were set up to record the El Nino event. And they've been recording sea surface temperature, air temperature, humidity, U-wind and V-wind, just the two wind direction and strength, basically, coding of wind, year and the lat and long, the buoys. They've been recording since the early 1980s. I've just got 2 years of data that I've pulled out for just about 3 or 4 buoys over here to show how we might explore missings. Yeah, so just about over there I have a few pieces of information. And I just pulled out data. This is data that I use in my undergraduate classes sometimes to show the difference between a normal year and an El Nino year. So green is normal, purple is the El Nino. And it was 93 that was a pretty normal year, and 97 was a major El Nino event. Here I've got sea surface temperature and air temperature plotted. And this is humidity and air temperature. So colors coding year. These lines of points here are the missing values. This is a GGOBI default. So if you're using GGOBI, it handles missing values very nicely because it plots the missing values in the plot, but at the edge of the plot. So you don't lose them. A lot of visualization software will just not plot missing values. And then it's hard to know, where they are. I think maybe I should use. Okay, so these points along the bottom here are the missing values, and the same in here. This line of points and these ones, those are missing values in those 2 variables. The structure is fairly specific. So these are missing on air temperature. Okay, so they're plotted in the margin 10% below the minimum data value. And so these are only missing on air temperature, although these ones in the corner here, these are also missing on sea surface temperature. But this tells you immediately that there's a relationship between the missing and not missing, right? Because if a value is missing on sea surface temperature, it is also missing on air temperature. But you don't have the reverse happening. Right, so if a value is missing on air temperature, it may be present in sea surface temperature, but not the other way around. So missings on sea surface temperature are also missing on air temperature. That immediately says that you have, at best, MAR, missing at random, because there's a dependence relationship. Right. And there's more than that too. So most of the missings here are in the 97 year, and there's only a few missings in 93. So most of the missing values are on that 97 year. That's also a dependence relationship. So we know that we don't have missing completely at random. So we should be using some information from other variables in order to impute the missings. Right. So it may be missing at random, we hope, and not the worst case scenario. Alrighty, and so here we have cases that are missing on humidity. These are cases that are but present on air temperature, and these are cases that are missing on air temperature, but not on humidity. They're present on humidity, and the ones in the bottom here are missing on both of the variables. Okay. Right, one thing that you can do if you have your missing values plotted in the margins is make a rough comparison of the distributions. Okay, so if your distributions are fairly similar, then that makes it easier to do the imputations. Right. So, but if you have a different spread of values in the missing cases than the non-missing cases, then it makes it more complicated to do the imputation. So here I've got some missings on air temperature, and let's look at the spread here relative to these guys. So these are the complete cases on both, but I just want to look at the spread in this direction to make a comparison between missing on air temperature and not missing on air temperature. And it's pretty good, I think. It's pretty well spread out between the two of them. So it looks like it matches reasonably well the complete case data. So that's a nice thing. And there's not enough cases here to be able to make any assessment of that. Over in this, these variables, so these are the missings on air temperature in relation to humidity. And again, it's a pretty nice spread of, at least these purple ones are pretty well spread out. Maybe it's a slightly bit smaller, but it's pretty close. So the distributions of missing versus not missing are fairly similar. So that's a really nice thing. And the same with missings on humidity. These ones are pretty well spread out, the same sort of spread as these. Okay? So we'd be able to say that it's not MCAR. Right. Okay, one sort of caveat. This approach doesn't work when you're using the multivariate methods that we've talked about the last 2 days. So parallel coordinate plots, the tours, you can't really plot the points in the margins. You can, but it doesn't really help you understand the structure. With parallel coordinates, you'd end up with a lot of lines going way down to the bottom. With the tour, you end up with lots of clusters. So it just gets distracting. So this is where you really need to have the shadow matrix, and so that you can highlight missing and not missing in different patterns, and then look at the multivariate plots. So here's a representation of the shadow matrix. On the horizontal axis, got missing on humidity. 0 means the value's there, and 1 is the value's missing. And vertically, we've got missing on air temperature. Again, 0 is complete, and 1 is missing. So I've only got 0, 0, 0, 1, 1, 0, 1, 1 in here. But I've used a little trick that we do sometimes, is to spread the points out. So we've got a block of points in here and here because I've jittered the points. The word jitter just means to add some random noise, just add a little bit of random uniform value to that. That way I can still see all the points in here and get some sense for. But this here is 0, 0, they're complete cases. These are missing on humidity, but not on air temperature. These are missing on air temperature, but not on humidity. And these ones are missing on both. So I only have 3 cases that are missing on both variables. All right, based on that, then I can highlight. So I'm going to pick the points that are missing on air temperature, but not missing on humidity, and link that to the other plots. Right, so those orange squares are these orange squares in here. And this is a picture of the 2 wind variables, right, U wind and V wind. And U wind and V wind are all complete. There's no missing values on these 2 variables. But we want to know the relationship between the wind measurements when it's missing on other variables, right? So what I'm looking at is, if I'm missing on air temperature, what's the pattern in U and V wind, right? If the spread of these orange points is the same as the other 2 groups, so again, the green and the purple are just the 2 years. So we want to just try to look at the overall shape of those guys versus the orange ones. Are they the same? They're not quite, right? So this is where the data actually is slightly more difficult to deal with. So at least on the U wind, the missing cases on air temperature have slightly higher values than the rest of the data. That says if the U wind is higher, we're more likely to have a missing on air temperature. Okay, so that's a real dependence relationship. Okay, make sense? Any questions? All right, we're going to go to an example. See if I can get these windows organized. So I'm going to look at the Mexico City data again. And I'm going to use the mice package for imputation. Has anyone used mice before? Okay, good. You might know more than me on it. It seems to have quite a few ways to impute missing values. I'm first setting up the shadow matrix, and then I'm going to combine what I have is I've got the matrix of actual data, and then I'm going to add the shadow matrix to that. So that way I can easily look at the missing, not missing, versus other variables. Right. So we're just going to explore the patterns of missing to start with. I'm going to use the library Canvas. See if they've got it set up.
I have a question.
Yeah.
I forgot if you told us if Canvas work on Linux.
Yeah, Canvas will work on Linux. Yeah. It's really hard to work with the projector because the windows are so big compared to the screen. So I have to resize them all. Okay. Okay, so what I have is ozone, the sulfate, wind, humidity, and I'm looking at missing versus not missing on the average temperature. Okay, so my new variables in the data set that contain the missing versus not missing have got the dot miss label to them. Right, so I'm just going to highlight the missings on temperature and look at the other variables. Okay, so sulfate is a very right-skewed variable. All my missings are at the low values of that. Maybe that's quite reasonable because with the skewed distribution, we'd expect to see more values at the low end. So, so the missings are on the low values of that. For ozone, this is a little bit of a mismatch between the complete distribution and the missings, because all the missings are at low values, and the shape of that distribution is quite normal. And so that says something about the missings on temperature versus ozone. Wind, they're a little on the low side, but there's not that, well, they are fairly low values. And then on humidity, there's nothing in here. Okay, the reason for that is Canvas by default does not plot missings. Right, so Canvas by default doesn't plot missings. So it's a little bit of a nuisance, really. What it means is that if you're missing on temperature, you're also missing on humidity, right? So we don't see any here because anything missing on temperature is also missing on humidity, right? And it would explain the reason here that there will be quite a few wind measurements that are missing when temperature is missing too. Okay, so that would be a way to explore this data. We see some dependence relationship, so it means that we don't have missing completely at random. The missings seem to be dependent on some of the other variables. A lot of you are time series people, so the obvious thing to do actually would be to plot things by time as well. So I just made a very quick display of the day versus the temperature. And you'll see that the missings on temperature tend to occur in one chunk of the time period too. All right. So I'm going to close these down again, and I'm going to do some imputation, and I'm going to try to, so hopefully this works, but I'm going to run the imputation in different ways and have the missings just pop up automatically in the plots so that we can see the patterns. Okay, one thing that I forgot to mention with this data, this is a summary of any missings. So on any days, what variables have I got missing? Okay, and these are the cases where I've got complete data. So what days have I got data on everything? It's not that many for this data. So there's actually only 63 days in the 366 where I've got complete data. So there's missings everywhere, right? And there's even some that are basically missing on almost all the variables, all the climate and the pollution variables, but it's present on the mortality data. Okay, so it's good to get that summary for overall missings. But then I've got a number of bar charts that are the shadow matrix. This is humidity, missing versus not missing on humidity. This is missing versus not missing on the nitrous oxide. And this one's missing on, or not missing on the mean. Okay, so if I highlight the missings on mean, this is my parallel coordinate plot. So it's not quite there. But this is a parallel coordinate plot of all of the variables. That's temperature, humidity, wind, and the pollution measurements. These have been imputed. So in order to start this off, I just did I think that just a multivariate normal imputation as a default. And so those are the imputed values, particularly for the missings on the mean that we see. Right. Okay, I'm going to try to do an imputation. Okay. So I just ran the imputation scheme to use a mean for missings. Right, so you see the mean value now. If I'm using the mean, I'm using a constant value. So that obviously is a little bit problematic. if I look at the scatter plot, it's much more interesting. Those are my imputed values for the mean, for the temperature. And that's, if you're using mean imputation, you're basically putting a fixed value into the data. For multivariate data, it's really cute because you can see the missings here, but see this other row of points along in this direction? Those are the ones that were missing on the nitrate. Oh, I don't know how to say things. So what happens is that by using the mean to impute values, you're imposing a cross structure in your multivariate data. And you can imagine with 3 variables, you've got a 3D cross structure. So it puts this very weird structure into your multivariate data, generally. Okay, and so generally people are very dismissive of mean imputation. Generally, if you try to publish a paper where you've used mean imputation, your reviewers are going to be a little bit, they'll be very critical of that part. But in my perspective in practice, sometimes it's a simple approach and sometimes it works. Right? And sometimes you don't really need to do anything more complicated. For the data that I just showed you before, the El Nino data, if I only wanted to be able to predict an El Nino event versus a not El Nino event, if I put little cross structures into each of those groups and I'm building a classifier, I still get good results. So to me, one of the measures of how good your imputations are is how your results might change at the end. So keep it as simple as possible without changing results dramatically. So if you're using a classification algorithm and you're imputing separately on each of those classes, the mean might be a reasonable thing to do. Okay?
Is this the same data set that we used?
This is the same data set we just looked at, that we looked at yesterday. Yeah. So I was showing you imputed data yesterday. So I had actually gone through this process before putting that data together and deciding which method worked reasonably well. So let's run another one. There's a method called sample. Okay, and sample just randomly picks cases to impute. And so you should see that the spread of the imputed values will be more than the complete cases. For these 2 variables, it's not a big issue. There's a lot of spread anyway. But in general, if you just pick a random value, you'll change. So if you have strong dependency in your multivariate data, by just picking a random value, you'll corrupt that. And so you'll make the covariance and the correlation, the correlation will get much smaller using a random value. And with the parallel coordinate plot, you can see that they're all over the place. Right. Yeah, so they're still all over the place. In general, random imputation is not the best idea either for multivariate data because it doesn't take into account the dependencies. Okay, this one's using a normal but with a bootstrap approach. So this would be one of the more sophisticated methods for imputing. And I think it's quite reasonable in these 2 variables. It gives you values that are spread out all over the place. But one thing I notice that most of the methods have difficulty dealing with, so the multivariate normal imputation and this one as well, they all miss the high values on the, this is 2, I don't think that's quite right. So they all miss the high values when there's extreme cases. And so if we're going to be using one of those simulation methods, particularly with a distribution like the normal, if you don't have a normal distribution on particular variables, then you have to realize you're not going to be imputing those extreme values either. And so the method that I did use in the final result was a normal sample, but it was clear it didn't catch that full distribution of the skewed variables, the variables that were skewed. Okay. And one of the things that you, if you're using one of the simulation procedures, each time you run the procedure, you get a different result. So each time you run the procedure, you get a different result, and that's usually used to get some sense of the distribution of the imputed values. That's one that we would look at as well too. If you're going to use one of those methods, you would run it several times and just look at the results that you gain. And it's really from doing that that I realized that this area doesn't get filled in very well. Okay, I think I've said enough about missing values. If you have any questions, I can take them before we move on to the next topic. So this is
You say that this data set is the level of missingness, is it too extreme?
It's quite extreme, the level of missingness, yeah. And
there's no implication of that this is a normal way to handle data analysis in general, in which I understood that it was 360 records complete, and then total.
yeah, 366, and it's only 63 complete. Mm-hmm. And then those missings are missing all over the place. So you've got a lot of variables in this data set as well. So it may just be that you want to concentrate on just a few of the variables. You might not need to look at carbon monoxide, or if your early views suggest that it's not that important in terms of studying mortality. But so you could reduce the number of variables, and that might improve your complete case rate. But this one is fairly difficult data to work with in terms of missing values because they're all over the place. If we really do want to look at that full scope of the pollutions and the weather and the mortality, then you have to do something with that. Because it's temporal data, though, you probably want to try to borrow from the neighbours as well, particularly with the temperature. Actually, I did see if I plot that one. Okay, so this is a real test for time data, right? So this is the time axis. I'm sorry, I haven't got lines. We can't easily draw the lines in Canvas with the scatter plot. And this is the temperature. These are my imputed values. And you could see a problem straight away with that, right? Those really are kind of crazy values to be imputing for temperature there. So that, I think that would rule out that we probably shouldn't be using the normal model for simulating the imputed values. We should probably be using a nearest neighbours approach, particularly maybe nearest neighbours in time. Yeah. All right. Okay. Okay, so I'm going to move on to cluster analysis. I'm going to start with my music data. So I pulled my CDs from ABBA, Beatles and Eels, and three classical CDs, Vivaldi, Beethoven, Mozart, and one Ennio CD. into my Mac. I used a package called Amadeus, which is a music editing package. There's a lot more around these days, I think, but Amadeus is still pretty much free to use. And with that, I clipped the first 40 seconds from each of those tracks on the CDs. And those 40 seconds of audio I read into R using the tuner package. It's good for handling audio. And from that package, I made some calculations on each of the audio clips. So the full data, I ended up, yeah, I've got that here. Yeah. Okay, so in Tuner you can make a picture. So this is the a plot of the audio clip for the ABBA song SOS and Vivaldi. They look quite different, right? It's got left channel and it's got right channel. All right, and so it's this data that I'm summarizing, because working with the full time trace is just too much for the few music clips that I used. And we ought to be able to summarize those patterns with just a few variables, I think. So I had 62 music clips. And in the original summary of the data, I created 72 variables because I included both the left and the right channel. In the end, I boiled it down to just 5 variables because 5 seemed to do an amazingly good job at the task that I wanted to do. So I just had the variance and the average and the maximum. And I looked at the periodogram and picked out the first few. This is really imperfect. I don't think you should recommend this to anyone, but it was simply enough to get a pretty good sense of differences between the music clips, and we'll see that in a moment. Okay. And so what we're looking for are how the music clips are similar to one another or different from one another. Because I had type of music in the data as well, I use this data for classification as well, whether we can classify the rock music from the classical music and from Enya. But we're just going to use this for clustering here. So this is the data in a tour. Gosh, that's hard to see, isn't it? So the initial data is really dark, but I'm going in and brushing things that I see from different views, right? It's called the spin and brush approach to looking at multivariate data. Okay, it'll get brighter because everything will get brushed in a moment. So right now, I'm just points that have been floating out on their own have been highlighted. Those are the outliers or the extreme music clips. Thank you. All right, this is really messy data. So after all that rotating around, I only found the 4 points, except now I'm starting to say, okay, let's break this big chunk up into smaller pieces. So this is a bit of an elongated area, bit of a gap. I'm just going to identify that group and see if they stay together in the future, and this one here. So that big clump has been broken into 3. Then those 2 seem to be not like the others in that group. Highlight them and then keep watching them. Sorry? Oh yeah, I should say each dot is one music clip. So there are 62 dots in here should be. Okay. Okay, so in general, spin and brush approach can be used to discover clusters. So just spin if you see a group that's on its own, highlight it, and then keep watching. So for this data, I've really broken the data into quite a few chunks. The main features are those extreme cases, so there's some music clips that are very different from others. But the rest we've broken into rough clusters. Okay. This was a very difficult data set to work with. There's lots of other cases that I've seen where it's quite easy to decide how many clusters there are just by this spin and brush approach. But it's difficult in the sense that there's not big gaps. There's a big long continuum, so it's not big gaps in order to pull them out. All right, so you need to start with defining what we mean by similar. So there's a lot of different similarity metrics or distance metrics, and I'm just going to use Euclidean distance here, Euclidean distance with standardized data. So if I have some data matrix, I've got 3 cases and I've got 4 variables, then I calculate the distance between the 2 by looking at the difference between the pairs of values, squaring them, and adding those up. Right, so if I want to find the distance between this row and this row, I just take the consecutive elements, 7.3 minus 7.4, square it, 7.6 minus 7.2, square it. Right, so looking at these pairwise values, that's just Euclidean distance. And then I get the distance matrix. Right, there's many, many, many different ways to define similarity. And I'm going to start with hierarchical clustering. And with hierarchical clustering, I start grouping the music clips together based on the most similar. Right? So hierarchical's been around for a long, long time, but it's still amazingly effective for a lot of different applications. So I'm using the hclust function in R and the Ward's linkage method, and you can think about it as starting off with each of the music clips in separate clusters, and we're just joining them together sequentially until everything's all in one cluster at the end. So the dendrogram summarizes that joining of cases together at different distances. And what else? So I'm also just using Euclidean distance. I don't know what else. Anyway, the names of the songs are laid out here as well. Basically what this says is that I have a fairly large group of cases over here that are considered quite similar. And if we look at the names of those, some of these are Eels music, some of these are Beatles, and it's basically Beatles and Eels. Then I've got another cluster in here. This is primarily ABBA music, So there's a little cluster of ABBA, Dancing Queen, Waterloo. I think they're all ABBA music. Then this group, maybe this is much more difficult. These are quite mixed clusters. This is primarily classical music, except for Hey Jude, right? So these are all classical, except for the Beatles song, Hey Jude. And then this is a mix. There's a few ABBA tracks in here. There's some classical, and then there's some Enya music in here. This is a Vivaldi track, and it's sort of a little bit on its own. Most of the methods, that one comes up as being extreme case, and that was one of the ones that was identified as extreme. But again, this is a bit of a mixed cluster. It's got some eels, it's got some classical, it's got some Beatles, it's got some Enya, it's got almost everything. It hasn't got any ABBA, I think. All right, so that would be the classical, yeah.
May we know the 4 outlier points that we observe?
Yeah, we can. Right, so I haven't got that linked in here, and it would be hard to pull. I have to run the software again to find this. But V6 is definitely one. V2 is another one, actually. I think these couple are outliers, but we'd have to dig back into. So I can't tell that from here, but I would have found that out from the graphics to start with. Okay, so that's a classic way to look at your results. Those results don't look too bad, honestly, because we've got some sensible way to explain how it's been broken down. But we really want to know just how good is that result and how much the results might change if we use a slightly different method. So I'm sorry, you might have to turn the lights out again. So I've taken the dendrogram and I've cut the dendrogram at 6 clusters. So what does that give me? I think it comes through here, and then V6 is left on its own. So that's a 6 cluster solution. And on each of those clusters, I'm now going to look at the cluster in a tour relative to everybody else, and also the parallel coordinate plot to see just how they differ. It's primarily important to focus on the yellow, which is fairly clear, I think. And that's generally the switch with an interactive system. You want to keep everything really dull, except for the highlighted group. So that's why the rest of the points start off as being purple. So this is cluster 1, and this cluster is fairly low on, or it's labeled cluster 1. I don't know which of those ones were cluster 1. It's fairly low on the variance. It's very low on average. But they've got fairly high max values, fairly high energy, and very low this L frequency variables. If we watch it in a tour, so I'll run this in a moment, that group should stay very close to one another in every view that we see. That's a good result from the clustering. They're fairly tight in the parallel coordinate plot, so you should expect to see a fairly tight cluster in the tour view as well. One of the purposes is to help decide whether you need to have an additional cluster or whether sticking with that was enough. But if that group breaks up into 2 separate ones again, you might want to increase the number of clusters you choose. All right, so this is the second cluster. So here's one of the outliers is included in there. And we should see that one pop up. Alrighty, so this is one way to, I've decided on a cluster solution, now just let's cross-check and see how good it is. Whether whether I can stick with that or whether I maybe need to do a little bit more work. Right, this is another way to look at it. Okay, and so this is a representation of the dendrogram. So again, it's a bit dark, but this is a representation of the dendrogram flipped, right? So it's on its side. This is the top of the tree, but at 2 clusters. So at the 2 cluster solution. This is as far down the dendrogram as I decided to look. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 clusters. Right, so it's not the complete dendrogram, but it's in the range of solutions that I want to explore. Okay. And each of the points here have been spread out a little bit. So this is cluster 1, cluster 2, but the points have been spread out some. And we can track the flow of the points through the dendrogram this way, and then see how those clusters appear up in the tour. So I'm going to brush in the dendrogram. This is a cluster of points that was identified early on. It's stayed together as a cluster throughout 10 splits. So if we think about the hierarchical clustering in the other way, starting from top down instead of bottom up, that really you can run it either way, but I ran it from the bottom up. This way I'm looking at all points in one cluster down to all points grouped into 10 clusters, so going from top down. So that group of points or music clips, the algorithm thinks is pretty clearly a cluster because they're all grouped together through 10 splits. Whereas this cluster got broken up into 2 chunks. One of those chunks stayed together the whole time, so that algorithm's pretty certain about those ones together. And then this group got broken into 2 chunks. This one got broken into another 2 chunks. This one eventually got broken into a few with some outliers. Some in singleton clusters. Okay? And so I'm going to highlight these and then take a look at those clusters up in the top. And the purpose is to decide, okay, whereabouts should I decide to make my final solution? At 3, 4, 5, 6, 7 clusters. Okay? So these I think they stay fairly close to one another, and by then identifying these cases, we can go back to finding which tracks form that cluster as well. So this is primarily the this is the eels and the beetle tracks. This cluster down here these are primarily the ABBA clips. All right. So it's clear that those 2 clusters are quite good clusters. Let's look at further down in the tree. This is where there's a bit of a split to decide, do we need to make that split or not? So both are highlighted. You see that they did split into 2 chunks. So maybe we want to consider the 2 separate solutions. Okay, I think that's enough of a demo here. So we can link the dendrogram to the graphics, and that it helps to digest the results of the dendrogram and make some decisions about the tree. Oh, so I'm using gGoby here, but I'm going to demonstrate using Canvas with a couple of other data sets in a moment. So you can do that with both. Yeah. Any other questions? Okay, next one. So I've run 2 different algorithms, and I want to be able to say which one I prefer, which is a better solution between the two. Typically, you create a confusion table where I've got results from one method tabulated against results from another method. Here I did a k-means algorithm. How many people have done k-means clustering before? A few people. So k-means is just iteratively. I set k-means and then I group cases to the nearest mean, and then I keep working. So I reassign cases to the nearest mean and then recalculate means, and then reassign cases to the mean and then recalculate. So it's an iterative algorithm that basically it breaks up your data into equal shape clusters. Sort of uses basically, puts Euclidean circles around the data. And then the results from the Ward's hierarchical linkage. With the confusion table, what one method calls cluster 1, another method might call cluster 5. So the labels 1 to 5 are not meaningful. They are different depending on what method gets used, and so it just means that they have different labels for the same object. So the first thing to do is try to match up the labels with those so that you get on the diagonal most of the cases where they agree. Right? That would be agreement. And so in k-means, what k-means called cluster 4 was best matched to what Ward's called cluster 1. Okay? And this one's a bit simpler. What k-means called cluster 1 really matches what Ward's calls cluster 5, right? Because there's 14 cases here where both methods agree they belong together. The labels are different, but they agree that they belong together. So in comparing the two solutions, we'd look at that diagonal relative to the off-diagonal to get some percentage of how much they agree on. And so for these data, they agree on like 77% of the cases. So that's a pretty high agreement between the two results. Right, to investigate that more, to understand why they differ, we can put that confusion table into the interactive system as well. So this is a representation of the confusion table, and then I link that to the graphics. So here's the hierarchical clustering. So 1, 2, 3, 4, 5, according to hierarchical Wards. And then vertically, k-means 1, 2, 3, 4, 5. It's not ordered as before, but we can highlight the large clumps. Those are cases of agreement. And then the smaller ones, so this is a cluster of cases that they agree. This would represent disagreement. Right? So we might be able to understand why these two cases are considered in different clusters by highlighting those. Right. All right, let's do one more and then we'll have a break. Because I'm using the same data, and then I'll have a short break, and then I'll show clustering of the Mexico City data and actual National Research Council ranking data. We'll cluster that too. Another method that's really interesting to know about for clustering is a self-organizing map. How many people have heard of self-organizing maps? Anybody? 1? 2? Okay. It's a method that's come from the machine learning community, and it's a very, very cute method. it actually is, it's really gorgeous, but it's not that much different from the k-means approach. But the idea is quite intuitive. So in a general setting, it's basically you take a 2D net and you fit that 2D net through your data. Right, so you could think about a fishing net, and you're going to go and catch fish with your net. That's basically what we're doing. We throw the net into the data space, and we try to catch all the data points. And so all the data points get assigned to the nodes of the net. Those are your means, basically, and that's the similarity with k-means. But once you've got that 2D net structure wrapped through your high dimensions, you can pull it back out, sit it on the table and stretch it out, and then you get some proximity of how the observations relate to one another. Okay? That's something that we haven't got with hierarchical, with k-means. We just have these discrete blobs, cluster 1, cluster 2, but we don't know whether cluster 1 is more similar to cluster 2 or to cluster 5, or very different from them. Right? So self-organizing maps gives you these two things in one nice bundle. As a statistician, what we would do is probably use principal components analysis and then look at the clusters in principal components. This map from the self-organizing maps is an alternative to principal components analysis as a view of the clusters. Right? Okay, but it's very, very cute. Generally it's an iterative algorithm. So here's your net. It's usually stretched out in the directions of the principal components. You can see it's flat. As you increase the iterations, this net is going to pull into the data in different directions. So you're going to warp the net. And then once you've already got your model fitted, so that represents a model, lay it out on a flat sheet again, and you put the points at where they were collected, so where that net pulled the points in. And so this is a representation of all of them, where the high dimensional space in 2D. So this is a dimension reduction, like principal components would do. Okay, one iteration that it was very flat still. If you increase the iterations, maybe you can see a little, the net's a little bit harder to see the blue points, but you can see it starting to bend and warp to the data. .500 iterations. .1,000 iterations. So you can see this net that's all tangled up in the data. Okay, that's our model. So what we're looking at is a model in the data space, and if it's a good fit, that net should really stretch out to all the points to capture everything. Can you see it? Okay. So you have to worry about the iterations. But once you've got a final model fit, then you can make some summary. So here's a look at a final result using the self-organizing maps on the music data. And I think this is what's neat. Right, so I've got the points for the music clips, but I've also got the labels to show whereabouts those music clips actually fall. And the colors are, orange are the rock tracks, blue are the classical, and purple, there's just a couple of purple other Enya, new wave. And I think you can see a bit of a divide. So there are actually 36 clusters in the solution, but this layout gives you sort of a continuum which works well with this data. So the classical seem to be all down here. The rock seem to be more up in this area. So it has done a little bit of a divide of the classical and rock without knowing that information. Okay, so that's good. And then there's a couple of cases that are a little bit odd. Like, this is Hey Jude, out here. Hey Jude behaves more like a classical track than than a rock. And Enya is kind of pretty much in the boundary. All the 3 purple points, they're hard to see, they're kind of in the boundary. And that makes sense too. Enya's a little bit classical and a little bit rock. Right? Hey Jude is different because, anybody know Hey Jude? Yeah? Do you know why it might be confused as a classical? It's very smooth, but it starts off very smooth, and the first 40 seconds is piano music. So, yeah, I had to go back and listen to it again, but the first 40 seconds is piano music. So it makes sense it's classical. All right, I think we'll, so that's all linked to the map view as well, so you can just see how good that fit is. I think we should have a 5-minute break.